Let's see what we studied in the previous class. So in the previous class, we have studied the adiabatic amplification. In that, just we investigated the simple adiabatic switching of the amplifier circuit, which consists of two transmission gated and two NMOS clamps. So in that we analyzed the efficiency for the different charging times and the voltage swings, and we compared it with the conventional buffer. So here we need to know which is the adiabatic buffer. Say example, if you want to say this will be your transmission gate. So here we are having a one NMOS. This is nothing but your adiabatic buffer. So here only we will give the input. So here we will take the output. This will be your Y, this will be your Y bar, then this will be your X bar. Why we are connecting the clamp circuit in the sense, because in the output we are having the load capacitance. So when I have load capacitance, we need a path to discharge. Because here the very important thing, the adiabatic circuits, what we are trying to do in the sense, it's in the normal, in the conventional cinema circuit, we use a fixed power supply. But with the help of the fixed power supply, we cannot be able to reduce the power dissipation beyond the limit. Beyond the limit is nothing but the CL into VDD square. We cannot be able to reduce that. So what we need to do to reduce that only, we went for the technique called as adiabatic switching technique. So then that the circuits will be used like this actually. So what we are using in the sense here, we are going to recover the energy, getting back to the reverse logic. The meaning is reverse logic. We are getting back the energy towards to the power supply. So here the power supply which we are going to use is here, like we are going to use time variant power supply. That is what we are going to use. This is called as time variant power supply. Or we are going to use the pulsed power supply. That is what we are going to use. Then we see the operations of the adiabatic amplification circuit. In this we are seeing like how the energy will be energized and how the energy will be de-energized. So that is what we see. Once it is the charge is complete, then what will happen? The output signal will be remain stable and can be used for the next stage of the circuit. But when it will be de-energized in the sense, when I give the input or supply the VL like a voltage ramp 0 to VDD vacuum, right? When you are going to back to VDD to 0, at that time what will happen? The circuit will be de-energized. So, which was the earlier, some of the energy was stored in the capacitor that will be transferred back to the power supply during this de-energized time. So now what we'll do, let us continue with the session here. As we mentioned here, so both the transistors will be operating non-saturation, means this transmission gate will be turned on with the minimal resistance, because as we know that here the transmission gate, the PMOS and the NMOS, the PMOS will be connected to ground, the NMOS will be connected to VDD. So supposed to connect to VDD. So this will, the both the devices, the B and the N, will be in triode region. Between triode region. So when the voltage drop across this TG gate is very small. The voltage drop across, so I can say voltage drop across the TG is small actually. So which is the indented for adding, which is the indented region? This is the indented region for adiabatic circuits. Okay, now what we'll do, let us model the conductance for n mass. Okay, let us model the conductance of n mass. Okay, so first, as we know that how we can denote the conductance here for n mass, it will be denoted as Gn, because here the notation, the conductance is nothing but what? The conductance is the inversely proportional to resistance. Keep remember, the conductance is inversely proportional to resistance. That is 1 by R we got. So we will write as the Gn is equal to the conductance, that is Gn will be is equal to Cn by Kn VDD minus V channel minus VTH. We take it as this equation number 1. Where you need to know what is Cn. Just here I will represent actually the Cn is nothing but a Cg actually, because sometimes they may say like this, what is Cg or Cn, I will say the Cn is nothing but gate capacitance. The Cn is nothing but a gate capacitance. Then VCH, we need to know what is Kn also, right? So let me say here where Kn is equal to L square by mu n. Cn is over. Next we need to know what is Ch. VCH is nothing but average channel voltage. Then we know that VTH is threshold voltage. Then we need to know Cn. Cn is gate capacitance of the device actually, right? Already we said gate capacitance of the device. Then we need to know about the mu n parameter, because Kn parameters, no? So mu n is modality, where L is nothing but channel length. But we need to know what is Kn, right? The nothing but the Kn is nothing but it's a process constant or process parameter they will call process constant. Now similarly we have to write for for PMOS, the conductance for PMOS will be Gp is equal to Cp by Kp into VCH minus VTH. This is equation number 2. So here, because we in our adiabatic circuit we consider transmission gate. The transmission gate has PMOS and the NMOS. So for NMOS the conductance is the equation. For PMOS the conduction is this. So now let us see the sum of both. Right? So let me say the sum of two conductance may be simplified by selecting the width of the two NMOS. By selecting the width of the two MOS devices. So let us say equation 1 and 2, or we can equate, both are equal in the sense, then only we can make a sign. That is nothing but the ratio will be like Cn by Kn is equal to Cp by Kp actually. And Cn by Kn is equal to Cp by Kp. Then as we mentioned here, the sum of two conductance, right? The sum of two conductance means we can write as Gp plus Gn, right? So Gp plus Gn will be is equal to, you need to add the equation 1 and 2. When you add, so here I specified Cn by Kn will be is equal to Cp by Kp. Means what will happen? There's either we can consider P or we can consider N also. So I will write as in terms of N. Cn by Kn, both we need to add. So I get the first for this N mass will have VDD minus VCH minus VTH. Then the second for P mass we are having plus VCH, then minus VTH we are having. So now simplify this. This by short what I can write in this GPN I will write. They are common, right? It's a common. So Cn by Kn into VDD minus 2 times of VTH. So I will take this is thus equation number 3. Now from this I can say the on resistance of the transmission gate. The on resistance of the transmission gate, the TG, right, is independent of channel voltage. Independent of the channel voltage. Means on resistance in the sense I can say it is like I can say it is like R on. That is what? That is on resistance. The channel. So you can see in this expression. So this on resistance actually that is GPN is right. On resistance how can I write it? That is R on I can write, right? That is RTG. RTGR I can say on resistance. So resistance means this is nothing but your transconductance. So how we can write us in terms of resistance? It is like the inversely proportional. Right? So R on will be is equal to what? Inversely proportional means I will take that like Kn divided by Cn into VDD minus VTH. You can see here the on resistance is independent of the channel voltage. This 2Vh, right? This 2Vh. This will be valid only for, I will say this is expression number 4. I will say this is expression number 4. But this expression is valid when it is valid in the sense it's valid only both devices are on. Means P and the N. If both are on, then only the on resistance will be this much will be Kn by Cn. Next, what we will do? Let us calculate the energy efficiency of the amplifier. Energy efficiency of the amplifier. Okay. Now to calculate the energy efficiency of this adiabatic amplifier is first the dissipation is the dissipation in the amplifier caused by first charging. Okay. first charging and then discharging. Charging one load capacitance CL. So now let us consider that is energy dissipation, that is E, right? Energy dissipation is equal to, I am writing that this factor is nothing but, it is the factor called as, the name of the factor is shape factor. So I will write here what is the name of this factor. This is shape factor. How we can read this means we have to read as psi. Okay, this is like the psi actually. So psi, that is considered energy dissipation. E dissipation will be psi RC divided by T into C into Vc of T the whole square. So this we took from the adiabatic charging from there actually. Okay, so E dissipation will be is equal to psi into RC by T, where you may need to know like what will be this psi, right? So this psi, that is psi, it is not a epsilon, it is a psi, it is a psi symbol. Will be is equal to this nothing but actually, because you may need to know what is psi actually. This psi is actually like a 0 to d I of theta the square d theta divided by I tilt of t the square into t should be greater than. This is the psi actually. This I of theta is nothing but this is took from the adiabatic charging actually. From there only it has come. Like to find the energy dissipation in resistance from the time from 0 to t. So there we might have calculated, from that only we got, or we might have calculated the capacitive voltage as a function of time. So there we may get that expression. From that only we have written this. This is nothing but your shape factor. So we have written the energy dissipation. Next, after that, so the load we have to write as the energy load. Okay, let us write the energy load, that is E load, because here you need to see charging and discharge, right? How much the time it's taking here, the same amount will be taken. By symmetry I can say it is twice. So E load will be twice, right? So twice the, or I will write one thing here, RC is the right as this R. This R is nothing but simple, I can say this R is nothing but your the on resistance, that is RG, or I can say on resistance, R on. This C is nothing but your load capacitance, that is C. We need to replace this C also will be nothing but load capacitance C here. So we have to replace all these things. We have to write the expression here. So let me write 2 times of psi RTG, or I can say R on, anything you can write, RTG into CL, the same expression writing, right? CL by T into CL into, what about the VCC? That is the output capacitance voltage. That is nothing but your VDD only, because during the charge time it will be VDD, right? It's a VDD square. Now we can substitute the Rn resistance, or you can consider this is the equation number 4. Substitute for RTG in equation 4. So we'll get us E load is equal to 2 xi by T into Kn divided by Cn 10 VDD minus 2 times of VTH into Cl square, because Cl into Cl square, into VDD square. This is we consider as equation number 5. So this will be your E load. Okay, energy load. This is the energy load. Additionally, what we need to do, we have to the parasitic effect, such as the C diffusion. I can say, let me put that way. Additionally, because any circuit you could take may have the parasitic capacitance. Additionally, the parasitic effect. The parasitic effects such as C diffusion, that is diffusion capacitance of the transmission gate of the TG and clamp end device. It will contribute to the total CL actually. So note, we are neglecting the parasitic capacitance. We are neglecting. So what we'll do? Let us take notation. Let us consider something their terms 2%. Let take your VDD is equal to m times of VTH, because we are considering VDD is equal to m times of VTH, and we are taking the time constant, that is tau n will be is equal to Kn divided by VTH. Okay, two consideration we are making. Let us consider VDD is equal to m into VTH, and tau n is equal to, that is tau n is nothing but so we may know that the tau n is nothing but it's a time constant actually. It's equal to Kn by VTH. Then the above expression or T load. So T load expression, you see that we have to substitute, okay, or we have to rewrite the expression. Rewrite the equation 5 after substituting the VDD and the tau. Okay, so what you do? Let us do that. The above expression, that is E load is equal to 2 psi T into Kn divided by Cn into, what we are doing in the sense, still we are not substituting, we are rewriting the equation number 5, just some for our convenience. So VTH into VDD by VTH minus 2 CL square VDD square. This is a rewritten of equation number 5. Okay, so we have not done anything newly over there. Just we return the, or for our convenience to make the substitution, we have written like this. Okay, so now what we will do, the same expression, let me take here 2 this then 2. Now the tau 1, what is the tau 1 is Kn by Vth. So the Kn is there, this Vth is there. So these two will come as tau n by T. I hope you got it right. This one as tau. Next, what will be next we have to write? Again into, so see that Vd by Vth, from this expression you can see this. Okay, from here only we can say Vd by Vth is equal to m actually. So let us do that. So what I will get in the sense, into 1 divided by Vdd by Vth is nothing but m. So m minus 2, then Cl, see, Cl divided by Cn, because the Cn is bending, right? Cl by Cn. The Cl square will be Cl into Cl into Cl into Vdd square. So now you can see this. This will be your separately took. This is, you can see the Cl, the ratio, the Cl by Cn is nothing but, where the Cl is nothing but your load capacitance. This is load capacitance, we know clearly, correct? This is load capacitance. What about this? This is all nothing but the internal node capacitance. So I can say this will be stage wise. This will be the next stage, this is the previous stage. Okay, so if I say Cl by Cn, this will be your next stage. This will be your previous stage. Okay, sometimes you will make cascade the amplifier circuit. At that time, the second stage, like if I say simple example, let me take, it will be very clear for you. I will take one inverter here. I am connecting the one inverter here. So here we are having the capacitance. Here we are having the capacitance. Here we are having the capacitance, because here also it will come like this. But you can see, if I consider for this inverter, this is the output, the final output only we can call as load capacitance. So now here this capacitance is nothing but a gate capacitance, means the internal node capacitance or the input capacitance for this node, for this inverter. Next, this is for your first inverter capacitance. So C1, this will be your C2, this will be Cl. That is what normally what we will do in this sense, we will go for like a Cl plus summation, the Ci they will call C1 plus C2. In this way only we have to find out the capacitance, total capacitance of rope. So now we got it, the yield, the load energy, right? 2 times of psi tau n by T 1 by m minus 2 into Cl by Cn, Cl into Vd square. I'll take this equation as this equation as 6th. I will consider this equation as 7th. Okay, so now what we'll do, this is in terms of this equation. Okay, let me see. This is this expression in terms of VDD. Okay, if we want, if VDD is known, then we can do. So same thing we can write in terms of VTH, because see here it's the absence of VTH actually. So you can do two ways, right? One is the way is VDD, the other one is VTH expression. So what same the way, what you have to do, you have to, instead of taking here VTH common in this E load expression, you have to take the VDD as common, then you have to work out. So you will get the expression as, because or you can write, right? The U load will be the E load will be 2 psi tau 1 by T into, here we will get m square by m minus 2, we'll get like this, into the CL by Cn into Cl into VTH square will get. So here we can stay separately, this will be separate. See, the only variation here is this VDD here VTH, then 1 by m minus 2, here m square by m minus 2, only these two. So this is expression number 8 we can take. So now from this you can make a dissipation like, if the dissipation is power dissipation is reduces linearly with the increasing the T. So dissipation is decreasing linearly with the increasing the T. See here this T, right? I can say this term, if I increase, automatically what will happen, your power dissipation will get reduced if I increase this T. What is this T? This T is nothing but your time ramp, I can say, like slowly what increase the voltage, right? That is what this one we can say. Since the VDD is equal to m times of VTH actually. Since the VDD is equal to m times of VTH, so the dissipation will be increases only linearly with the voltage swing actually. At the time only voltage swing your will be get increases. So I can say here this is for your VTH swing, right? I say here if I want to say VDD, this VDD, see this VDD is nothing but what? It's a m times of your VTH actually. Correct. So simple. I can say from this the energy is also dissipated to drive the input capacitance. Energy also dissipated to drive the input capacitance. So the input capacitance normally will write as Cin or Ci 1, 2, 3 like that. Okay. Now if you consider when the energy is taken into account, the dependence on T and VDD is affected. The energy is taken account. Then the dependence on T, and the VDD is affected. So this is about the on resistance and the energy. So now what we will do, we need to study about the stages. If it is a single like okay, here I have to go for stages, amplification stages. So here we are going to study two things. That first is we are going to study one stage adiabatic buffer in conventional system. In conventional system, Second, we are going to say two-stage adiabatic buffer in conventional system. Then one more we are going to say it's a fully adiabatic system. So this one stage and two stage and all I can say it is a partially adiabated. Okay, partial or one stage, two stage, or you can consider just like so now what we are going to do, we are going to study as like a one stage adiabatic buffer and two stage adiabatic, because you can cascade it, because as you know that amplifiers you can stage wise, if you get increases, so you can able to rate, you can able to improvise the circuit. Right. So now what we will do, let us go for the first. Let us go for the first one, that is one stage adiabatic buffer in conventional system. Okay, so one stage adiabatic buffer already I drawn. Just let me draw the diagram. One stage adiabatic buffer would be like this. This is your input X. This will be your X bar. Then this will be your Y. This will be your Y bar output actually. So here we will have the capacitor. Even here also we have the capacitor. Okay. So if I say this will be your load capacity, output to output, like this also will be load capacitance only, because we are connecting the input over here. If you are connecting the input over here, in the sense we will have the gate capacitance. That is why we said here we studied about CG. That is nothing but we said as CN, right? I can say CN, better gate capacitance for this. You know that how it is a buffer circuit. You know the buffer. What is the meaning of buffer? Buffer is when I give the input as 1, 0, I get the output as 0. When I give the input as 1, you will get as 1. Means the buffer, whatever the input you give, that only will get as output. So now when I give X is equal to 1, this both will be on. If the circuit both are is on, in the sense what will happen? What are the value is there Y bar, the same value will get in the Y. Means you previously you should think, you have to assume that the Y bar is pre-charged already. Initially it was pre-charged. You have to think in that way. Or it is not pre-charged. If it is pre-charged initially, then what will happen automatically? If X is equal to 1, then this will be on, then the same 1 will get, so this will be charged. But by the time even this also will be on, if it is on, you may think it will start try to discharge actually. So before that only it will drive the another circuit. So we need to apply the input here only. See, when you a single buffer, this is a buffer actually. Normally they won't use the single stage, one stage. That is the reason we have to go for two stages. When I go for the two stages, then automatically we may use the power supply, something called as VA. You might have seen in the previous diagram. Right? So now, very important thing in your circuits, normal, conventional CMOS circuits and all, so there will be much more power dissipation will be in the internal mode capacitance than the load capacitance, because the internal load capacitance are more. But your CL, that load capacitance always will be very large than the internal node capacitance, always. So always your CL will be very greater than CI actually. So now first what we need to do here, we need to analyze. First let us analyze. First analyze the case, in the sense your input Vin is equal to VDD. That is nothing but your Vin. Okay. So where is the V? So assume the case, so that all the input energy is dissipated. So that all the input energy. So the input energy will specify as E in is dissipated. All the energy input. So what you have to do, you have to make a assumption, that is, let us assume that the total input capacitance of the input, okay, the total input capacitance of the input, that is the total input node capacitance of the input is directly proportional to the gate capacitance. Directly proportional to gate capacitance, or I can say Cn, right? Cn of the TG, that is transmission gate, NMOS device with constant proportionality to alpha square. The alpha square is nothing but what? What is it? It's a scaling factor. As we know that previously we studied, the alpha is nothing but a scaling factor. Okay, alpha square. So this is scaling factor. Okay, now what we'll do, let us take example. So let us take a example. If no parasitic capacitance we are considering, capacitance are considered, and the gate capacitance, that is the Cn, okay, of the clamp device NMOS. So Cn is for your gate device for N transistor. Cp means gate capacitance for P device. The clamp device is neglected. So if you are not considering the parasitic capacitance, then the gate capacitance of the clamp device will be neglected. So from that, can say the alpha is equal to Cn plus Cp divided by Cn. So this here I will consider equation number 1. Alpha is equal to Cn plus Cp by Cn. So the dissipation caused by driving the output of one of the transmission gate is given by the energy, that is the input energy, right? That is E in. So E in is equal to, what's the E in? Alpha into C in into, not C in, Cn. Okay, Cn into VDD square. That is the input energy. The input energy will be Cn alpha. Alpha is the scaling factor, as we know. Then Cn is nothing but the gate capacitance. Then VDD is nothing but your power supply voltage. So we'll consider this is the equation number 2. Now what we need to do, we need to calculate the total energy dissipated per cycle. Total energy dissipated per cycle for one driven output. One driven output, that is E total. So the energy total, that is the E total, will be is equal to, total energy will be the input energy plus the load energy. That will be your total energy, input energy and the load energy, where the input energy is nothing but alpha Cn into VDD square. But now what about the load? The load is nothing but already we written in the previously. I hope you remember, because of the on resistance. If both the transmission gate is on, then the load will be, what is the load? The load will be 2 times of psi into tau 1 by T into 1 divided by m minus 2, then Cl divided by Cn into Cl into VDD square. So I hope you remember this. This already be written. This will be like this. Okay. So this is the equation number 3. You can say this whole thing is something. This is the expression we took the load we consider in terms of VDD actually. So now here the equation number 3, this equation actually, it's a trade-off in adiabatic CMOS circuit with the conventionally driven inputs. Now here, if with this increases, width of the device, it increases, then the input capacitance will be increases. Keep it in mind always, right? If the width of the transistors get increases, then the input capacitance also will be increases. If the input capacitance is increases, then the dissipation, the energy charging the load will be decreases. Charging the load will be decreases, and charge the input will be increases. Increasing will be charge in the input. Okay. So energy dissipation, that is nothing but what? The charging the load will be decreases, but the charge input will be increases. So now we have to calculate what is the minimal power dissipation. That is the minimal power dissipation, like the minimum energy. So minimal energy dissipation which dissipation is achieved by choose the device size. Choosing the device size. So even your device size also will play an important role here. Device size. So the optimum NMOS CG, that is gate capacitance, CN optimum gate capacitance will be written as CNOPT, that is optimum gate capacitance is nothing but 2 psi alpha into tau n by t into 1 divided by m minus 2 into CL with the root power 1 by 2. Remind. So this will be your the optimal gate capacitance. Because this is very important. Optimal gate capacitance is nothing but this much. So from this, what we have to do in the sense, we have to calculate the E total. So let us write the E total now. What is E total? E total is nothing but E in into. Okay. So now what we are going to do in the sense, we are going to consider the E in is equal to E load. So as you know that E total is nothing but what? E total is equal to E in plus E load actually, right? So now here we are E in is equal to E load. So it is nothing but what? It is nothing but E load plus E load. So it will be like twice the E load. So now we need to substitute and we have to get the expression, that is E total is equal to 2 times of alpha into that C was there, no? That is Cn was there. Instead of Cn, we have to write as Cn OPT we have to write. Okay, instead of E load, sorry, here I will write E in, it will get it be E in only. So here also it will be like E in only. Then 2 times of E in. Okay, 2 times of E in. So anything I can write. So I'll write in terms of E in. 2 alpha 2 NOPT into VDD square. You consider this is equation number 5. So now what you do? Substitute the equation number 5 in 4. Substitute equation 5 in 4. So what you will get now? Sorry, substitute equation 4 in 5. So we'll get the total as 2 times of alpha. We know that 2 into alpha into, then you do this 2, that is alpha into tau n by t into 1 by m minus 2 into CL into outside will be VDD square. Now what you do? Take this 2 alpha inside the root. So if you take inside the root, what will be now? 2 will become 4, right? 4, then alpha will become alpha square, then 2 psi alpha into tau n by t into 1 by m minus 2 into CL. Finally here we will have VDD square. So now what you can do? Alpha. So as you know that, right, this is term is like this one we brought inside actually. Now this alpha square and alpha will get cancelled, then will get us 4 into 2 8. So I will get us 8 into alpha into tau n by t into 1 by m minus 2 into CL. So this will be in the root. into VDD square. So this will be the total energy, equation number 6 I will write in terms of, this is in terms of VDD. So same we need to write in terms of VTH. So already we got the E in terms of VTH also you have to write. So similarly I can write, so E total is equal to 8 sin alpha into tau n by t. This will not change anywhere, right? So this will become as m power 4 divided by m minus 2 into CL into VTH square. This will be equation number 7. So the equation number, this equation is very important. Which one? This equation number 7. Equation 7 is important for important limitation for adiabatic charging with conventionally driven the control signals. So because of the complete dissipation of the controlling gate energy, the total switching, because of complete, the total switching energy will scale as 1 by root t, actually scale as 1 by root 2 as opposed to 1 by t. 1 by t scaling of the energy dissipation epsilon, so that epsilon RC by t into C into VC of t the whole square. So this is nothing but your one stage adiabatic buffer for conventional. So in the next class we'll study about the two-stage adiabatic buffer in conventional system.